Okay, so today we're getting into chapter 3. Oh, I always forget. This classroom has the no good screen. Oops. Okay. Is that? I hope that's legible. Okay. So chapter 3, we're talking about numeric summaries. For numeric data. All right. Just give me a second. This is lecture 4 into the month of April 4th. Okay, so if we just step back and we think about the big picture of statistics, we say we have some entity called the population, which is too big to be observed directly. So what do? We take a little piece out of it. This little piece is called what? A sample, okay. And our sample, could have, say, like n equal to 200 observations in it or something. Maybe bigger, maybe smaller, it doesn't matter, okay? And we can look at our data table and look at all 200 rows and say something about it. We could draw another sample, and maybe that sample also has 200 rows, and we might look at all 200 rows. Now, our brains aren't usually good at comprehending all of this information all at once. So what's often helpful is if we summarize all 200 observations, all of that information in just a few numbers that we can then use to make comparisons, okay? So instead of comparing every single row from one sample to another sample, we can summarize our data with just a few key numeric summaries, okay? So comparing, all of the rows in our data set or in our sample to all of the rows another sample we may prefer to use numeric summaries. Okay, and another key way to say numeric summaries, these are also called sample statistics. Okay, so we are basically summarizing 200 rows or n rows of information into just a few numbers. And we're familiar with stuff like this all the time, okay? So in your lives today, there is a number that, well, many of you care about, maybe not all of you, called the GPA, all right? And this value it's a single number that's supposed to summarize your entire academic performance, okay? So we are familiar with a numeric summary called the GPA. This is our grade point average. This is a single value that summarizes your academic performance. Okay, so my understanding is that we have a few students visiting from South Africa with us. Is that right? Are you guys here? You mind? Yes. Okay. So wonderful to have you guys with us. I don't know if in South Africa, do you guys use something called a GPA, or is there? Is there a number that they? Something similar? Okay, so in the US, your highest GPA, at least in college, is a 4.0, right? This is like the best you can get, all right? Maybe in some weird circumstances, a 4.3 for UCLA Law School or something strange, but okay, in general, it's like 4.0 is the best, and then, 0 would be the worst if you failed all of your classes, and that's like your nightmare scenario, right? Okay, now, if you wanted to apply to medical school or something like that, you're probably very concerned about the GPA that you have. And the GPA is useful, right? If you had to pick classmates for a group project, and somehow we published your GPA next to your name, you would probably want the classmates with a 3.8 or a 3.9 or something, and you probably would not want to pick on your to be your teammates the ones with like a 2.0 or lower, right? In general, okay? Now that's might be unfair, but if you just had the single number, you'd probably be very discriminatory in picking your classmates or teammates, okay? That might be completely unfair because as far as we know, somebody could be working multiple jobs and juggling many responsibilities, and that's why they can't get high grades or whatever. There's all sorts of things, but it is still useful instead of having to look at a student's entire academic transcript and look at like, oh, this student got this grade in this class and this student got this grade in another class. We can just say, oh, boil it down to a single number. You have a 3.8, you have a 2.2. Based on this number, I'm going to think that this student with the 3.8 is generally a better student than the student with the 2.2, okay? And maybe that's unfair to do, but that's kind of how things go, because for the sake of convenience, we often boil things down to just single numbers, right? You probably don't have to worry about this for another few years, but if you want to go out and purchase a car or something, people are going to say things like the important thing is your credit rating, right? And the credit rating is just this number, kind of, based on some arbitrary formula that says, oh, this is how trustworthy you are at paying back money, okay? And it's just this number, and it's like, oh, you have a 790? Great, we'll lend you money. Oh, you have a 600? We're going to lend you money, but we're going to charge you a lot of interest type of thing, okay? It's just, whether we like it or not, this is kind of how the world works, because rather than sitting people down for like a 10-hour interview to get the inner workings of someone's life, a single number is often useful, okay? So the GPA, that's all it is. A single value that summarizes your academic performance, okay? Does not capture the entire story. Okay? But it's still useful when making comparisons between students. Okay. And the pros and cons of using these numeric summaries is that to make big decisions is that you have people trying to game the system, right? Perhaps when you were in high school, I hear this story often, is that honors classes were worth 5 points or something, okay? And so you would take the honors classes, and then you would try to avoid taking things like PE, because how dare, getting an A in PE would only give you a 4 and bring down your grade point average. You have ridiculous scenarios where people are trying to game things, game the system in order to keep this arbitrary number as high as possible. And when people talk about improving your credit rating, they say, oh, you should do this and you should do this, but not do this. And it's like, why? Why does this matter? And it's like, oh, because that's how the these numbers are determined, and this is what happens. So anyway, we have numeric summaries for specific purposes. And many of these we are familiar with. So we have, GPA, credit rating. Okay. We can also like compare countries. Economic power with, things like GDP or GDP per capita. You have other things like the HDI, human, Gini index for economic inequality, all sorts of things, okay? These are just numbers that, based on some formula that some person came up with, decides how to compare things, okay? For sports, you have baseball season's just starting up. That's exciting. Any baseball fans? Okay, yeah. All right. Okay, you have batting average. Okay, now batting average is kind of fallen out of favor if you are into like sabermetrics and stuff, but batting average or what, on base percentage or whatever, if this means nothing to you, then don't worry, okay? Those of us who like baseball will care. The rest of the world doesn't, okay? And so these have specific purposes, and they're useful, okay, if you're trying to make comparisons from one baseball player to another baseball player or things like that. Okay, is it fair to say this person's so back when batting average was the way we rated things, maybe it wasn't so good because someone might have been very good at defense or something, and then you had like the Mendoza line and things like that. Okay. So we have, so these are, for specific purposes, and we also have generic, kind of like useful in any situations, okay? Generic sample statistics that can be used for any set of numeric data. Okay, so, and these can be categorized into kind of two broad categories. We have sample statistics, excuse me, that summarize central tendency. Okay, so these would be values like the mean and the median. Okay, and then we also have sample statistics that summarize dispersion or spread, and these would be things like the standard deviation, or the interquartile range, the IQR. Okay, so these are, so these other ones, GPA, credit rating, these are specific purpose-built numeric summaries. Okay, these other ones, mean, median, standard deviation, IQR, these are generic. They're still very useful, and they're useful for any numeric set of data that we have. Okay. Can I flip to the next slide? Anybody still writing? You good? Oh wait, do you want me to go back? Okay, you're good. They'll be posted online as well. All right. Okay. So, you know, our textbook says when our numeric data is symmetric, okay, and what does it mean for our numeric data to be symmetric? Yeah. Evenly distributed? I would argue that's more uniform. So symmetric would be values that are extremely low are equally common as values that are extremely high. Okay? Or so values on the low end are just as common as values on the high end. Okay? So our textbook says when numeric data is symmetric, meaning values, you know, much lower than average. Then maybe I'll just use the word typical. Just want to make sure everything is still legible. Everything's still legible? We're good? Okay, great. Thumbs up. Thank you for that thumbs up. It's always very reaffirming when you guys give me thumbs up or you nod your head whenever I just ask, like, does this make sense? And you guys, like, nod your head. It's like, yes. But then when you just kind of stare at me, I'm like, man, this is hard. So you know, smiles are always nice, you know. Okay. I try to smile a lot. All right. Values. I don't know why. Okay. Values much lower than typical are just as common as values much higher than typical. If no, okay. All right, well, this kind of throws off the flow of the sentence here. Our textbook says when numeric data is symmetric, we might prefer to use the mean and the standard deviation to summarize our data. Okay, and if our data is skewed, okay, we might prefer to use the median and IQR. Okay? And what does it mean to be skewed? So skewed distributions mean you might have extreme values on one side, but not on the other side, right? So skewed would be extreme values on one side, meaning very low or very high, but not on the other. All right, but the truth is that the mean and the median, the standard deviation and the IQR, they can be used for any set of data, whether it's symmetric, whether it's skewed, okay? It's just, there's certain aspects about these things that might make them preferable for these situations, okay? Yeah. You might prefer to take a big car if you're going to do a lot of shopping, but can you go shopping in a coupe? Sure, you can, okay? So there's just any scenario that you want to do, okay? So the mean and median and standard, okay, mean and median, or, you know, standard deviation and IQR can be used for any numeric data set. Good? All right. Okay. Guys, I still see people writing, so I'll give you guys a moment to catch up. All right, so let's we'll start with the mean first, okay? Okay, and I think you guys are already familiar with the mean. You probably learned about it in middle school. Okay, so the mean is, you know, this can be thought of as the quote average. Okay, so of our data. You know, the term average is a bit ambiguous. They probably also taught you that in middle school when they said, you know, here's the mean, but then there's also the median, and they both count as average. But generally, when people say the average, they generally refer to the mean. Generally, okay? So symbolically, we use this, okay? X bar, this is read as X bar. And this is the, this means the, this is the sample mean, okay, or, you know, the mean of our sample. Mean of a sample of data. Okay, whereas, you know, later on in the course we'll talk about the mean of a population, and that uses a different symbol here, okay? But we have X bar, the mean of our sample, and the way we calculate this is sum of X divided by N, okay? So this just means sum or add the X's, the X values, and then divide by N, okay? And I think we're already familiar with this. N being our, what? Sample size, right? Okay. Kind of our conceptual definition of the mean is going to be the balance point of our data. Okay, so let's say we had 4 children, okay, and the ages are 2, 4, 6, and 16. Okay, I'm going to draw a dot plot of this. Okay, so let's start off at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So the dot plot, I'm going to draw these fat dots on each of these data points to kind of emphasize what I'm talking about. So 2, 4, 6, and 16. Okay? So imagine these are big stones or big rocks, okay, on a board here. And if I want to put this on a seesaw, where should I put the little triangle, the fulcrum, so that our thing stays balanced? Okay. Well, you know, if I put it over here, what's going to happen? The thing's going to tip over, right? Okay, and if I put it over here, the thing's going to tip over the other way. So where we want to put it is the mean, okay? So the x bar, if I add these up, 2 plus 4 plus 6 plus 16, that gives me 28, okay? So 2 plus 4 plus 6 plus 16, this, and I divide by how many I have, this gives me 7, okay? So my mean is 7, and this is exactly where I want to put the fulcrum, okay? And maybe it seems like it matches your visual expectation. So right here, I have x bar equal to 7. This is the balance point. Balance point, meaning if this were a seesaw, and I put a big rock over here, far away, and I put 3 rocks, so all of these rocks are the same size, okay? But if I put one very far away over here, I would need 3 that are close by over here to counterbalance. All right. So does that visually make sense to you guys? Okay. I hope. Thank you. Thank you for that smile and head nod. So, okay. So this is what we mean by the balance point, or the average of our data. Okay. If we looked at this data, would we say our data is symmetric or skewed or what? Skewed, and in which direction? Skewed to the right. Okay, so our data is skewed to the right. Okay, so according to our textbook, it might not be preferred to use the mean in this case, okay? But I think it's a good illustration of this concept of the balance point of the mean, okay? And if we said, you know, what's the typical age of these 4 kids? That's a hard question to answer, right? Like, what's the typical age? You'd say, well, I got 3 kids that are like around 4, 5, and then I got 1 old kid, 16, right? Like you can't give one number that captures the story, right? You know, if these were your children, you'd be like, oh yeah, I got, oh, you know, your kids are so great. Oh yeah, well, and I also have 1 kid that's super old too. So it's, you know, to try to capture a bunch of information with a single number, that it's challenging. Okay, so, you know, it's like, tell me something about yourself in a few words. I don't know. Don't ask me such hard questions. Okay, so here's another scenario, like why might we use the mean in certain scenarios, or, you know, when might it not be? Okay, so imagine we're in a small town. Okay, small town, maybe you know, there's a mining town. Okay, and you walk into a diner, all right, and in the diner there are 6 people sitting there. Okay, and you know, you feel like you can just ask anybody questions, and you say, hey, how much money do you make? Okay, so we say, you know, what is your income? All right, and then so these 6 people, they're like, oh, sure, I'll answer your question. I make 60,000, and the other guy's, oh, you too, me too. And then and you go through, and like 5 of the people make $60,000. This is a 0. Okay. I can't count anymore. All these, and then the last person's like maybe the shift leader. This person makes $70,000. Okay. And okay, and then so you say, oh, well, what's the average? The mean income here would be what? We add these up. So this is like 370,000 divided by 6. 370 divided by 6, and we get 61,000 $667, okay? Something like that. Okay, sounds good. All right, let's say rich person, I'm using Bill Gates. Does Bill Gates have a lot of money every year? I don't know, something. Okay, let's just pretend, we're gonna pretend his annual income is $10 million. I don't know. Is that too much? Too little? I have no idea. Too little? Okay. All right. So this is like not quite as good as Bill Gates. Okay. We'll call him Will Gates. It's like the same person. Okay. All right. Okay. So Will Gates, Bill Gates' less rich secret twin, walks in. He makes 10 million. Okay, so we say, what's the average? Okay, so now we say, okay, we got $10 million, and then I don't want to write all these numbers down, so I'm going to draw a box. Okay, so we're going to copy these over. Okay, so what's the average? The mean here is now going to be, we add all of these up, and it's going to be, what, 10,370,000 divided by 7. Okay, so what's that? 10,370 divided by 7. Yeah, thanks. Okay, so the average here is now 1.4 million. What is it? I can't read. Okay, $1,481,429. Okay. All right. Is this the average income of the 7 people in our diner? Yes, it is. Okay, I mean, by definition, this is the mean. This is the mean income. Does it feel representative of these 7 people? No, it does not feel representative. Okay, and so this is where we see that the mean is very much influenced by outliers. Okay, or extreme values. So the mean is a measure of center that is influenced by extreme values. Okay? And so, if you wanted to ask what's the typical earnings of people in the diner, it would probably not be very good to say 1.48 million. Okay, the typical earnings is something around $60,000-$70,000. Okay, and I think there was a case where something like this happened. There was like a small college, and in one of their brochures they published, our graduates make an average of $80,000 per year. Okay, which is like, oh, that sounds pretty good. What they didn't disclose was that one of their graduates was went on to be an NBA basketball player and made several $1 million a year. So the mean was definitely very, very much affected by that. Okay, so that's just a bigger version of what happened here. So in certain cases, it might not be preferable to use the mean in these situations where you've got extreme values. Okay, but in other cases, if you were trying to report the expenses of this company, okay, what are the company expenses, and payroll is one of them, and this company is set up this way, which I don't know how a company would do this, but one person makes $10 million a year, and the other, there's seven employees in the company, and then the other people make $60,000 or $70,000 a year. Would it be fair to say, oh, as far as annual expenses go, typical payroll values between $60,000 and $70,000 a year? Okay, that is technically correct if we're not using the mean, but it may not be fair to use if you're looking at it from another perspective. Okay, so So depending on the scenario, you might want to use the mean, you might want to use the median, depending on what you're talking about. All right? Is that good? Okay, so we'll talk about the median in more detail on Wednesday. I've got to cover the standard deviation, okay? Oops. Okay, so the standard deviation, okay, is a measure of spread all right, measure of spread or dispersion. And sorry, I should switch back to my black pen here. Okay. All right, and so as far as standard deviation goes, what we're going to, this is how we're going to define it. We're going to say the standard deviation is equal to the square root of the variance. Okay, and the variance, we're going to define it as the quote-unquote average squared distance from the mean. So this is a, so these are two good definitions to memorize, I think, okay? But keeping in mind that the standard deviation as a big picture concept is a measure of spread or dispersion, okay? And so let me tell you why the measure of spread or dispersion is an important concept to cover. Okay, so let's say we have two families. Both have 5 kids. Okay, and both families have an average age of children to be, so we'll say they both have an average age of 9. Okay, so both families, 5 kids, the average age of the kids in both families is 9, okay? Does life in both of these families necessarily look the same? No, and I'll tell you why. Okay, so we got family A, I don't know, the Adams family, okay? All right, the kids' ages, we will say, are 7, 8, 9, 10, 11, okay? So 5 kids, boom, 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 boom. And so you got 5 kids very close to each other in age, okay? We've got the Baker family. They were much more methodical and, well, I don't know, maybe this is the wrong word to use. Okay, so the 8 kids are 1, 5, 9, 13, and 17, okay? So both families, 5 kids, both families, the average age is 9. Does life in the Baker family look anything like life in the Adams family? Probably not, okay? Over here, I mean, the oldest child here can very much act as a caregiver for the youngest child, okay? This one's going, you know, getting ready to go to college. This one's still in diapers, you know. Over here, you know, you got everything happening together, okay? So, so over here, we would say high spread, okay? The ages are spread out. There's lots of dispersion. And over here, we have low spread, okay? And rather than just using terms like lots of spread, little spread, okay? And over here, it's very clear with these numbers, okay? With these ages, because we can kind of visualize what this looks like. The standard deviation is, it's just a number that gives, it's a number that we can assign to this concept of high spread versus low spread, okay? So, so let's take this definition of the variance and the standard deviation. So the variance is the average square distance from the mean, and we'll calculate the variance and the standard deviation for the Baker family. So we're going to, again, say the variance is the quote-unquote average squared distance from the mean. Okay, all right, so let's look at the Baker family. Their kids are 1, 5, 9, 13, and 17. Okay, what is the mean age? The mean age is 9. Okay, so what is the distance from the mean? So we're going to have distance from mean. Okay, how far is this kid who is 1 year old? How far is his age from the mean, or her age? 8 years away from the mean, okay? Then the 5-year-old is how far away from the mean? 4. The 9 is 0, and the 13 is 4, and the 17 is 8 years away from the mean. Okay, are we okay with getting 84048? Okay, or another way I could, just subtract 9 from each of these things, okay? If I wanted to, okay? All right, so that's distance from the mean, okay? We can now have squared distance from the mean, okay? So, whether you just say how far is it or whether you subtract and you assign numbers, it doesn't matter because when we do the squaring, the signs go the right way, right? So squared distance from the mean. Okay, so what is 8 squared? 64. 4 squared is 16. 0 squared is 0. 4 squared is 16. And 8 squared is 64. Okay, so these are now the squared distances from the mean. So far, so good? Okay, so if I wanted to take the average square distance from the mean, I would what? I would add these up and divide by 5, right? That's what I would do if I wanted the average square distance from the mean. But I have quotes around average, and so what we're going to actually do when we do the quote-unquote average square distance, we're going to add them up, and rather than dividing by 5, we're going to divide by 1 less than 5. We're going to divide by n. So the average square distance, this is add them up and divide by n minus 1. Okay, so rather than dividing by n, you're going to divide by n minus 1. Why do we do this? The answer is it's complicated, but if you are interested, it's called Bessel's correction. Okay, Bessel's correction. You don't need to know this. If you plan on becoming a statistics major, then sure, you should learn why we do Bessel's correction, and it will be covered in one of your mathematical statistics classes. Everybody else in the world, it doesn't matter. Just know that this is what we do. We add them up and we divide by n minus 1 rather than n. Okay, so what are we going to do? We're going to do 64 plus 16 plus 0 plus 16 plus 64, and we divide by, well, we're going to divide by what? 4, right? Rather than 5, we're going to divide by n minus 1, so I get 160 divided by 4, and I get 40. Okay, so my variance, being the quote-unquote average square distance from the mean, my variance is equal to 40. Is that okay with everybody? Okay. So if my variance is 40, what is my standard deviation? My standard deviation, which we use the symbol s, s would be the square root of 40. And so I would do the square root of 40 is 6.325. Okay, and that is my standard deviation of ages in the Baker family. Does this feel satisfactory? Okay, so if you can remember that the variance is the quote average square distance from the mean, okay, we can figure out what it is quite easily. All right. Okay, so we'll do the same thing for the Adams family. Okay. All right, so okay, and the ages are what were they? 7, 8, 9, 10, 11. The mean here also is 9. Okay, so we're going to get distance from the mean. And so we have what? 2, 1, 0, 1, 2. Okay, and then we're going to do the squared distance from the mean. Which we square the 2, we get 4. We square 1, we get 1, 0, 1, and 4. So the squared distance from the mean, so our quote average squared distance from the mean will be what? Okay, so what do I do if I want to get the average of these numbers? Add them up, and then, but I would divide by what instead? By 4 instead of 5. Oops, I can't. It's hard to write numbers and say different numbers at the same time. Okay, so we have this. We get 10 over 4. This is my average square distance from the mean, so I get 2.5. This is my variance. Okay, so my variance is 2.5. Okay, and so my standard deviation is 1.581. Okay, so my standard deviation is 1.581. This is equal to the square root of our variance, 2.5. Okay. All right, and so this value, this is the standard deviation of ages 7, 8, 9, 10, and 11. And so if we look at the standard deviation here, we have 1.581. If we look at the standard deviation of the Baker family, it was something like 6.324 or something like that. Okay, it's not a coincidence that the standard deviation of the Baker family is 4 times larger than the standard deviation of the Adams family. Okay, so the standard, if we looked at the ages, okay, in the Adams family, the kids are all spaced out 1 year apart. In the Baker family, the kids were all spaced out 4 years apart. Okay, and so it's not a coincidence that the standard deviation for the Baker family ends up being exactly 4 times larger than the standard deviation of the Adams family. You don't need to worry about the mathematical theory as to how that worked out, but keep in mind that the standard deviation, all it is the number that summarizes our spread. Okay, it summarizes, are the values quite similar to each other as they are in the Adams family, or are they quite spread apart as they were in the Baker family? Okay, and so if you can remember the definition that the variation is the quote average square distance from the mean, and that the standard deviation is the square root of the variance, you're in good shape here. Okay, we'll see you guys on Wednesday.